Today is April 27th, 2021, and we are going to have a conversation about biogeochemical cycles. That's a big word there, but we're going to break it down and make it make sense. The objective today is to analyze the flow of energy and cycling of matter, such as water, carbon, nitrogen, and oxygen, through ecosystems. So we're going to get into some chemistry today, and you all will revisit these terms next year during your chemistry class. But we're going to give you a good preview of what that class will entail. The essential question that we will seek to answer by the end of today's lesson: why is the cycling and flow of energy and matter important for the sustainability and health of the ecosystem, or of all ecosystems, right? Because we know that Earth is a huge collection of thousands of ecosystems. So it's the fourth day of our 9th unit. Just as a reminder of our timeline going forward, we do have our Unit 9 exam scheduled for this Friday, April 30th. And that also means that your Unit 9 assignments will be due this Friday, April 30th. Going forward, we have one more unit of new material. So it's kind of hard to believe where we are in the semester at this point, but we only have a little bit more to go. That last unit is literally just one standard, but it'll still take us, I think, 7 days to get through it. So we can expect that our Unit 10 exam will be on May 11th, and I think that will be our last day in person before testing begins. From that point forward, we will spend plenty of time reviewing everything that we talked about in the course so far. This will also give you all an opportunity to get extra credit. So we will take a mock EOC exam, which is not going to hurt your grades at all. It can literally only boost your grades. So it's going to be a cumulative exam, 60 questions, just like the EOC exam will be on May 26th in this class. And if you do well on it, then you'll get plenty of extra credit for your formal exams that you've taken in the past. All right. So does anybody think they can repeat what I just said? Good. Thank you, Lance. All right. So I just want to make sure we're all clear. And what's happening later this week? What day is the test? Friday. Thank you, Abina. Just want to make sure we get that. Tomorrow, of course, is a virtual day. What that means is that class will begin a little bit earlier than normal. So I'm going to make sure I send out a remind message to you all, as well as the link for the class meeting. It'll be the same link. Class will be shorter. We're going to go over some topics that I think are a little more simple, so as not to waste your time. And then we'll come back Thursday, last day of learning, and then Friday will be the exam. So that's our timeline going forward. We're in the final stretch. We are definitely in the final stretch. Let's get started. So that word biogeochemical, I promised that we would make it make sense. And actually, you're going to do the work of making it make sense. So I'm going to hide the names here on your screen. For all of those of you who are in the Nearpod, you should have this open-ended question. What do you think the word biogeochemical means? Give me some ideas. I would love to see 100% participation today. Everybody who's in the Nearpod, let's make sure we got our brains flowing, our thinking caps on. Let's get some answers going. Let's try to keep high energy. I know it's, again, final stretch. It's kind of hard to stay high energy, but I'm going to push you all and just be loud. Interesting. Okay, we got one answer. Bio equals life, chemical equals harmful. Certainly chemicals can be harmful, but not inherently so. A chemical process with animals. True, we're getting there. How chemicals affect life or the environment based on the words bio and geo. Yeah, so we know that this implies some type of interaction between living organisms and their environment. Living chemicals in the world. Okay. A pathway by which a chemical substance is turned over or moves through the biotic and abiotic compartments of Earth. That's good. That's good. I want to make sure we understand that though, but that's a good, strong answer. So thank you for whoever submitted that. Chemicals in nature or in the planet and the impact they make. We're at 40% participation. I want to see some more submissions here. Why join if you're not going to actually participate? How chemicals affect geographical life? Good, and then that's one direction, and then we can also go the other direction. How does geographical life affect chemicals? 67%. I think I missed one. Chemical substances which occur within living organisms. True. True, true, true. Okay, so let's take 15 seconds to submit an answer. $73. Okay, one more answer. Something between living and non-living and the effects. Between, I think I'm going to trust to mean that that's not like actually like the physical space between, but like how they interact and the effects of those interactions. Good. And then one more answer. I don't know where it came from. 80% is not bad. Let's keep going though. Keep those thinking caps on. I'm going to be on you today for a lot of review. So biogeochemical, let's break it down. That's how we understand words that are foreign to us. We try to break them down. Bio, of course, that refers to living things. Yes, ma'am. Biogeochemical cycles. That word at the top, and then just cycles. Bio refers to living elements. And then we've got geo, which refers to elements of the planet Earth. And of course, geo doesn't necessarily mean land. Geo could also refer to the atmosphere, which is, of course, the gases that make up the space above the land. It could also refer to the hydrosphere, which is the water that is present on the Earth. And then lastly, chemical. Of course, this refers to that thing, the periodic table of elements that's behind you all. Again, I've had you look at it a couple times. That's going to be a big part of your chemistry experience next year as you break down all the information that chart gives you, because it looks like a bunch of gibberish, I'm sure, right now, but it's got some really, really useful information there. We're going to talk specifically about the atoms and molecules that make up, that are essential for life. And today we're going to talk about the cycles of carbon and nitrogen in our biosphere. Okay. All right, so here's the first definition that I would love for you all to write down. This is the definition we're going to go with. Somebody came really, really close to this. I'm not exactly sure who it was, unless they would like to reveal themselves, but we had a really good definition. Biogeochemical cycles are natural pathways by which essential elements of living matter are circulated between abiotic and biotic factors. So, Paris, can you tell me what abiotic means? What does that word mean? Would you say? Okay, So not related to, so yeah, that's a kind of a complicated way of saying not living. Abiotic is something that is non-living, and therefore biotic is the opposite, something that is living. So of course we know that there are interactions between those two camps, non-living substances and living organisms. We're going to talk more about those interactions today. What does it mean to be circulated? What does that mean in this context? Okay, what does that word mean, circulated? What'd you say? A circle word? What do you mean by that? You could be on the right track. I just don't. I'm not sure exactly what you mean. Good. That's a good way of putting it. Yes, the circle of life. I mean, that's probably a phrase you all have been hearing since you were little kids. But what we're going to find out today is that it's so true. Does anybody else have any thoughts about circulated? Abina, I thought I saw you raise your hand. Ashanti, I thought I saw you raise your hand a couple minutes ago. No, that wasn't you. Okay. Somebody else. Janelle, you have any thoughts about circulated? What does that mean? With what? Like in your body? Yeah, that's a good example of circulation. That's true. So I guess what we're talking about here is how things are moving and exchanged from one area to another. So our circulatory systems in our bodies exchange gases. You take in oxygen, goes into your lungs, the lungs pass it off to your blood. Your blood is also picking up carbon dioxide from other areas of your body. They drop those back off to your lungs, and then your lungs get rid of it when you breathe out. So that's a great example of the exchange that takes place in any circulatory system, including the environment, what we'll find out today. Okay, so we talked about 4 biological macromolecules way back in January with our very first unit of the class. So in this activity, I want you all to match up the pairs of the terms. I want you to match the atoms of each macromolecules, of each of the 4 macromolecules. And then I also want you to match their monomers as well. If you finish early, might be a good idea to write these. Well, actually, it'll come on the next slide. So never mind. Good review, good review. Good. We've got some folks who did 8 out of 8 and 9 tries, 10 tries, 11 tries. That's excellent. That's where we want to be. Believe it or not, I had some students in my last class at 50 tries. I didn't know what to do. Good. So let's take 30 seconds to finish up. 30 seconds. And I'm sure you all are starting to have some thoughts come back to you. What I've mentioned in my last class, when we have downtime like this in class and you all are done, great opportunity to flip through some of your notes. It's not enough just to write them. You want to make sure you're dedicating 10 minutes, even if it's 10 minutes broken up, 3 minutes here, 3 minutes there. You want to make sure that you're going over your notes. That's how you make sure it sticks. That's how you make it salient. 15 seconds, 15 seconds. Mm-hmm. Okay. All right. So here's kind of like the summary of what we just did. We've got the macromolecules. Again, there are four of them: carbohydrates, lipids, proteins, and nucleic acids. Each of them has kind of their own chemical makeup. Carbs and lipids have the same three. And in fact, those same three are present in all four macromolecules. But carbs are special because we see them appearing in a 1 to 2 to 1 ratio. That means if there are 5 carbons, there should be 10 hydrogens and 5 oxygens. Proteins are special because they have nitrogen, and nucleic acids are special because they have both nitrogen and phosphorus. And then we've got the monomers there on the right side as well. I'm sure this feels like a long time ago that we talked about this for the first time, but this is going to be a big part of your EOC exam in one way or another. So we got to make sure that we are going over it. Does anybody want to take time to write this down or to take a picture of this? Or am I good to move on? Are you writing it? Okay. I think that's a great idea. This is a big bang for your buck slide here. If you can remember this, you're in a good place. For the rest of you who are choosing not to write, excuse me, I want you to start thinking about some examples, because on the next slide, I'm going to ask you to give me some examples. What is an example of a carbohydrate? What's an example of a lipid, protein, nucleic acid? Two, three, four, five, six, seven, eight, nine. Excuse me. We good, Paris? Okay, cool. All right, so as promised, here's a collaborate board. I want you to give me some examples of carbs. You don't need to give me an example for each one. Just give me some stuff as it comes to your mind. What examples can we remember of these four macromolecules? And make sure you tell me what it's an example of. So if it's, for example, glucose, make sure you say it's an example of carbs. Pasta is a carb. Thank you. Bread, our bread is a carb. Yes, our source of carbs. And if you, I forgot to point this out, but on the last slide, I did have good. I don't know who sent that here. Thank you, JT. So on the last slide, I did have the letters OSE underlined in glucose. The reason for that is that most sugars do end in the letters OSE. And JT reminds us that sugars are carbs. Thank you, Astrid. Milk has a lot of carbs too. Banana has carbs. We've got a lot of examples of carbs here. Examples. Oils are lipids. Thank you, JT. Anything else we can think of? There are some examples of nucleic acids too. Can we remember any of those? Hmm. What else? Can we think of any others? Here's a protein. Someone said enzymes. Yeah, enzymes. Where are you seeing that? Oh, really? What? That's weird. It looks like yours froze after bananas. Interesting. Okay, sorry. I'm not sure why they're. I'm glad they're coming up for you all, but I can't see them on my screen. So we just want to have some examples in our mental arsenal. The EOC exam is not going to come out and say, here's a protein. It's going to come out and say something like a hormone, blah, blah, blah. What is a hormone made out of? And then you'll have to say amino acids because you'll know that a hormone, there it is. You have to know that a hormone is a protein. That was weird. Good. Excellent. Good job, folks. All right, so just keep these examples in mind, and we are going to continue to review this concept as we go. It's being really slow now. All right. So there are two laws of physics. So we're covering everything today: biology, chemistry, physics. These two laws define the biogeochemical cycles. And I'm just going to ask that you write down the portions that are highlighted. So the portion that's in the parentheses there. The law of conservation of mass states that in a closed system, matter can be neither created nor destroyed. Or in other words, mass remains constant in a closed system. Sarah, are you taking notes? Are you typing? The other law is the second law of thermodynamics, which states that without energy input, entropy will always increase. So systems become more disordered without the input of energy. So I like to think about the second law of thermodynamics in terms of my bedroom when I was in high school. So, throughout the course of the week, you're busy, or I was busy. I'd have practice, I'd have different events, I'd have homework. So, I'd start off on Monday, my room would be pretty clean. And then I'm throwing dirty clothes in one spot. I've got clean clothes in another spot. I had books and notebooks in different places in the room. So by the end of the week, my room was not in good condition. Um, that's that demonstrates that things get a little bit messier as time goes on. Even if I went out of town for a week and I returned, there might be more dust on surfaces. There might be a spider or some other insect somewhere in the room. So even without my dirtying the room, it gets less ordered over time. And this is the idea of entropy. Entropy always increases. That means that chaos, um, messiness always increases over time. The only way to reverse that is if you actually put energy into the system. We can think about this on a cosmic level too. Since the Big Bang, which of course is still a theory that we cannot prove, but since the Big Bang, everything has been moving outwards. And so the entire universe is getting more chaotic. Things are moving further and further away from one another. There are, over time, more explosions, and those contribute to chaos as well. But we can also think about it in terms of a single teenager's bedroom. Things get messier over time. The only way to reverse that is to put energy into cleaning it. So another way to think about it, I'm sure we've all had this experience. The air conditioning is on. You open the door, and here comes an adult. What do they tell you? Do you open the door to the outside, and it's hot outside? What do they tell you? They say, close the door. Why? You're letting all my air out. Right. And in reality, it's not that you're letting the cold air out, it's that the hot air is flowing in. And so that is what we call a spontaneous process. Heat is always going to flow from hotter areas to colder areas. The only way that you can reverse that is by putting energy into it. So you would need like a fan to blow the cold air out. It requires energy to do that. In other words, or for the most part, the only way that the heat is going to move is from a hot area into a cold area. Okay, so that's again the second law of thermodynamics. Spontaneous processes increase entropy. Processes that don't use energy, they contribute to disorderliness. Okay, so because of these two laws, the chemicals that are needed for life are constantly circulating between the geosphere and the biosphere. Because we cannot create new matter, and because things become more disordered without inputs of energy. The geosphere is the abiotic regions that make up the Earth. So that could be the atmosphere, which of course is all of the gases, the lithosphere, which is the actual surface of the Earth. It could be the hydrosphere, which is the water on the Earth. And then that even references something called the cryosphere. Does anybody have any thoughts about what that might be? The polar ice caps, good. And then the biosphere is the sum of all ecosystems on the planet and all of the biotic organisms that make up those ecosystems. Okay. So on your screen, hopefully this is visible. It's probably not super visible on the screen in front of the room, but you can see in this image the carbon cycle, essentially. And it's showing the movement of carbon from the atmosphere to terrestrial sources, from human sources back into the atmosphere. And then it's also showing some interesting places where carbon is stored. So actually, I'll give you guys like 10 more seconds to take a look at this before we take this quiz. So you notice I see the word photosynthesis. I see phytoplankton that are doing photosynthesis. I see the word respiration in a few different places. So that's what this next quiz is going to ask you all to remember. It's been a while since we talked about photosynthesis and respiration. So again, we got to jog our memories a bit. Okay. 2 minutes, 6 questions, 20 seconds per question. Okay, we are about halfway, a minute left. Should I have given more time? Under 30 seconds, under 30 seconds left. Okay. So we struggled a bit, to be expected. It's been a while since we talked about these terms. Let's take a look at some of these questions. So number one, which of the following is the correct equation for photosynthesis? You may remember that photosynthesis and cellular respiration are literally opposites of each other. So if we kind of reverse the two reactions, then they're equal to one another. So photosynthesis, we got to think about the plants doing photosynthesis. They take carbon dioxide and they also need water. They need a constant water source. And they turn it into glucose. They turn it into food. That's why we call them autotrophs. And in the process, they produce oxygen that we can use to breathe. Again, the opposite of that is cellular respiration. But this time, we're also creating something called ATP, which is energy that our cells can use. So we take glucose that and not just us, but all living organisms, all living organisms take glucose. They take oxygen gas that they get from the atmosphere. They produce carbon dioxide. They also produce water in the process, but their main objective is to make ATP, to make cellular energy. In what form does carbon exist in the atmosphere before it enters the biosphere through photosynthesis? So I'm trying to emphasize the relationship between the two in this question. The atmosphere is, of course, the gases that are above the surface of the planet. And then the biosphere is all those living organisms that make up ecosystems. Those that do photosynthesis take carbon dioxide. That's the gaseous form of carbon. They take that carbon dioxide and then they use it to make glucose. In what form does carbon exist in the biosphere before it enters the atmosphere through respiration? So this is the solid form of carbon. This is glucose. And then, of course, it's used to make ATP, and carbon dioxide, which then enters the atmosphere again. Okay, in which organelle does photosynthesis happen? Photosynthesis happens in chloroplasts. And respiration happens in mitochondria. So those are organelles. Again, that's unit 2 stuff. So we had a little bit of unit 1. This was a little bit of unit 2 and unit 4. We're trying to get some more review going just to jog your memories as we get closer to this EOC. All right, so if you struggled here, don't beat yourself up, but just make some notes, make mental notes, but also some written notes as well that might jog your memory and you can return to as we move forward. Any questions about this? Okay, we're good. Okay, so back to this image. So the cool thing about this image, we can see in several places there are numbers in parentheses. The numbers represent, as it says at the top right, the gigatons of carbon per year. Gigatons. So 1 gigaton is 200,000 pounds. So we can see we're exchanging a lot of carbon in our environments. But the ones that have the numbers in parentheses represent what are called carbon sinks. And these are places that store carbon. So the amount of carbon isn't necessarily changing very often here. The ocean is a huge carbon sink. And we're not just talking about the surface of the ocean where most of us do our swimming and most of us eat our fish from. We're talking about the deep ocean. Is a huge carbon sink. There's a lot of carbon that's just kind of trapped there, but that can be released and will be released over time. Same thing with the fossil pool. This is where we get our natural gas and our coal from. So what used to be trapped and what was trapped for thousands of years, even while humans existed, over the last 250 years, we've tapped into it. And so we're releasing a source of carbon that has, for the majority of the history of life on our planet, been untapped. And now we're putting it back into the atmosphere. We'll talk more about that. The atmosphere itself is a carbon sink. It has a lot of carbon stored inside of it. Soil is a carbon sink, a big one. And then also trees. Rainforests are huge carbon sinks. All right. So as we tear down the rainforest, as we tear down forests in general, we're removing trees, and those trees are no longer able to take in carbon dioxide. So again, all of these things are contributing to us flooding over the last 200 years or so, the atmosphere with carbon dioxide. Okay, we can see here photosynthetic organisms that are taking carbon dioxide from the atmosphere and using it to make glucose. You should definitely write that down, especially if you struggled in the previous quiz. Photosynthetic organisms, and this could be plants, but it could also be, as we're looking on the right side, phytoplankton and algae. Those are organisms that live in water, but that still do photosynthesis. So in general, we just call them autotrophs. They take carbon dioxide from the atmosphere and they use it to make glucose. Okay, is anybody still writing? Okay, so try to break this down. I'm sorry, I didn't realize how much text this was, but just try to summarize or paraphrase this. All living organisms get glucose. Some of them get glucose through photosynthesis, others get them or get it by eating other organisms. For respiration, they all need glucose for respiration. And the goal of respiration is to create energy. In respiration, they release carbon dioxide back into the atmosphere. That's a part of respiration. Okay, so we can see that happening in this picture as well. Organisms are doing respiration and they're releasing carbon dioxide back into the atmosphere. So you could literally just write organisms release CO2 into the atmosphere. Okay. Nothing to write down here, but this is just important to note. There are some organisms that release more carbon in other forms. It's not just through breathing out and releasing carbon dioxide. So, for example, cows, when they poop, their poop has a high level of what's called methane in it, and methane is also not good for our atmosphere, and at least not in high amounts and concentrated amounts. So, it's not just the release of carbon dioxide, but other sources of carbon that then make their way back into the atmosphere. And humans are adding more carbon to the atmosphere through various activities, like the burning of fossil fuels, the laying of cement, and the ways that we've changed our living landscape as well. So as I think this is the last slide for this image, but if you look at the top, it says the atmospheric carbon net annual increase is 4 gigatons of carbon. So we've thrown it out of balance now. The atmosphere is taking in more carbon than it's getting rid of. A lot more, 4 gigatons. That is, I think that's 800,000 pounds of carbon. A gigaton. Yeah, maybe even 8 million. What's giga? Can't remember. Okay. Another important part of the carbon cycle is decomposers, like fungi, certain bacteria, and worms. These decomposers break down the organic matter of dead organisms and return their carbon to the soil. So trees, leaves die. You know, in the fall, the leaves fall off of trees. In the spring, especially in snowy places, you don't see just a whole bunch of leaves, like, you know, piled up 10 feet deep because over the years, all of the leaves have fallen. The leaves will eventually decompose and they become nutrients for the soil so that more plants can grow or that the trees can grow even larger. Or they become food for not only the decomposers, but other insects as well.
This is what I try to argue
When what?
whenever I'm over
Yeah, yeah. It's good fertilizer for the soil. I'm just going to leave it.
I think the largest living thing on the planet is a system of fungus in some forests.
Hmm.
Like miles, just straight mycelium under the ground.
Yeah. Okay. Are we good here? And then other sources of carbon into the atmosphere. For whatever reason, they didn't include it in that last graphic that we were looking at. But of course, human activities, such as burning fossil fuels, as well as natural activities, such as volcanic eruptions, introduce greenhouse gases into the atmosphere. Carbon dioxide, methane, and nitrides. Once these are added to the atmosphere, they contribute to something called the greenhouse effect.
Why are power plants like concrete cylinders concave?
That's a good question. I don't know. Okay. Oh, Paris to the right. Okay. So the greenhouse gases that we just talked about end up becoming a part of the atmosphere where they trap radiation and heat. Now, some of them are meant to be there. Again, natural processes have put them up there, and they've become an important part of our upper atmosphere. And they trap solar radiation, and this is what actually keeps our planet warm enough to support life. But over the last 250 years, we have added way more of these greenhouse gases than really should be there. And so we're trapping too much heat. Not enough of it is escaping back into space. And this is warming the planet. And as the temperatures increase, the climate is changing. We're not talking about daily weather. That's important to note. Climate and weather are two different things. But the warming of the planet is contributing to a changing climate. Okay, we've got 12 minutes and a little bit more to cover. Told you today was going to be a rather long one. I appreciate you all. You've been troopers today. I want to keep that energy up. You're a quiet class. Typically, my honors classes are they tend to be more rowdy than my standards classes. Not you guys. Does it still feel weird to be back in school? Does anybody have special plans this summer? Where does he live? Cool. New York City?
No.
Okay. Okay. Well, that'll be fun. Okay, this is another collaborate board. So what I want you all to do here, in your own words, summarize the carbon cycle. So summarize the movement of carbon between the geosphere and the biosphere. Bonus points if you can use buzzwords: photosynthesis, cellular respiration, decomposers, carbon sink, greenhouse gases, blah, blah, blah. So let's take 3 minutes to do this. And then we'll wrap up with a little bit of talk about the nitrogen cycle. Ugh. Oh, my collaborative boards are not updating, or maybe you guys haven't. Can you see anything, Lance?
No.
Good job. Excuse me. I'm satisfied with this. Feels like we have a good grasp. 4 more slides, and then we're done. So let's see if we can get through it. The nitrogen cycle. Nitrogen is just that, not just as, it's pretty important. The atmosphere is 78% nitrogen, so huge amount of nitrogen gas in the atmosphere. It is obviously a part of proteins like enzymes, hormones, hemoglobin, and also nucleic acids like DNA and RNA. But it's not quite as important as carbon because carbon is omnipresent. It's present in almost every form of life. Nonetheless, we still focus on the nitrogen cycle because it is still needed for those 2 organic compounds. Nitrogen fixation is the process by which bacteria take nitrogen gas from the atmosphere and convert it into ammonia, NH3. It's called fixating. When you take something from its gaseous form and you put it into a liquid or a solid form, that's fixation. Okay. Let me see if I can paraphrase this for you. Sorry. Oh, I knew that was going to get you. One more. This is the last one, I promise. I'll go back, Paris. This is the last one. So there was no asynchronous assignment today. There is, of course, an exit ticket. I apologize that I didn't leave enough time for you all to do that. Tomorrow, again, we will meet earlier. I'm going to schedule some remind messages to go out just to remind you that we are meeting, I think, at 10 o'clock. And have a great day. Thank you, Melissa. Thanks, Lance. See you, Janelle. Paris, if you want to see that last definition. There it is right there. You are welcome. See you, Tay. See you, Abina. Yes, sir. Okay. Are they making you all come into school for that? Yeah. Okay. All right. Well, good luck. Thank you for reminding me. See you, Paris. Thank you.